moving to the right at the speed v sub p. All right, and we have mass flow rate coming in again at this station, and let's write down an expression for the momentum of the fluid coming in at that station. Here we're going to attach our inertial reference frame to this moving control volume, and since the control volume is moving at a constant speed, this is reasonable to do. All right, we got atmospheric pressure acting all around. We got the external force F sub A shown in this figure. All right, so we're ready to apply a similar balance equation as above. So we got mass flow coming in at this station, and it's simply the density times the area. And now sitting on the reference frame, which is moving to the right at this constant speed v sub p, I see the fluid entering this control volume at a speed Vj minus Vp, right? So Vj is the velocity with respect to the stationary reference frame, but since my reference frame is now attached to the moving control volume, it's simply Vj minus Vp. I need to multiply this by the velocity with which the fluid comes in as measured by my inertial reference frame. My inertial reference frame choice is this one shown here. So that's also Vj minus Vp equals sum of all the forces acting on the control volume, right? So it's negative F sub A, atmospheric pressure cancels out. I can rearrange this and solve for Vj, and I get this result. What I encourage you to do is consider taking this problem, part B, and solve this problem using the ground as my inertial reference frame, right? Using the ground as my inertial reference frame. I'll give you a hint. When you do that, you also have to worry about the momentum that might be leaving the control volume at this station. All right, so keep that in mind. You should be able to solve that problem. Here's an example problem in which we will apply two different control volumes. Right. So in the first part of the problem, we got a horizontal jet of water that strikes a plate of diameter d, and we want to determine the jet velocity if the force Fa that is required to hold the plate is given to us. And part A, the only difference is part A, the plate is held stationary, and part B, the plate is allowed to move to the right at a constant speed v sub p, right? So the plate is allowed to move to the right at this constant speed v sub p. So that's the difference. And so we've restated what's given, and what needs to be computed is simply the jet velocity v sub j given the external force F sub A that's applied to this plate. Let's look at the suitable control volume. In both cases, the control volume would essentially be using the rule, the control surface, we either know something or we got to compute something. All right, so keeping that in mind, the control volume for this problem is simply going to be the region spanning the fluid, and it also includes the plate itself, and the force external to the plate is shown acting on the control volume. And this is so the objective in this problem is to find this velocity with which the jet comes in. Second part, same control volume, except keep in mind that the control volume is actually moving to the right at a fixed speed v sub p. So that's the distinction over here. So let's look at the analysis for the first part of the problem. So we have a control volume. I've isolated that and shown we got inflow rate of mass coming in on this station right here. It also brings with it some x momentum, and so let's make sure we have the x direction marked here. So that's the x direction, and then shown on the control volume is atmospheric pressure acting all the way around, right? So everything is exposed to the atmosphere. Atmospheric pressure acts all the way around, and so the net effect is atmospheric pressure doesn't really play a role. And then finally, we have the external force F sub A acting on the control volume, right? So this sort of completes a picture, if you will, of the control volume, showing all the essential ingredients to solve the problem, right? So now we are ready to apply Newton's second law. We make the assumption it's a steady flow, so the unsteady term, the time varying term drops out, and so we got an inflow of mass coming in at station 1, and the inflow is simply the density times the area times the velocity with which the fluid comes in as observed by someone attached to this reference frame, and it's simply the velocity of the jet. All right, so because the reference frame is stationary, and the fluid just comes in at the speed v sub j, and then I need to multiply this by the velocity with which the fluid comes in at this station as observed by an inertial reference frame, in which case chosen to be the ground over here, and that's simply v sub j. So that gives me the total momentum coming in at station on the left over here, and it's negative because it's inflow, and there is fluid leaving, but this fluid doesn't carry with it any x momentum, so that makes it the only momentum inflow term that needs to be concerned with in this problem. And the right hand side is simply sum of all the forces acting on the control volume, which is acting in the negative x direction, so that's negative f sub a. Right? So we rearrange it and solve for v sub j. Right? So that's the way we solve part A of the problem. Let's look at part B. The control volume is the same control volume, except keep in mind this control volume is continuously moving to the right at the